So the problem that we have for crystallization is that a crystallizer is charged with 7,500 kilograms of an aqueous solution at 101 degrees Celsius, 28.5% by weight, which is anhydrous sodium sulfate. Then the solution is cooled, and during the cooling operation, 5% of water originally present was lost. As a result, the crystals of sodium sulfate decahydrate crystallize out, and the mother liquor is found to contain 18.2% by weight of anhydrous salt. So the first thing we need to do so that solving this crystallization problem would be a lot easier is we need to draw a block diagram. So since on the actual problem it is already given, so what we need to do is to fill out all the necessary informations that are um, missing, such as since it's already given that 28.5% by weight of anhydrous sulfate goes into the feed, so meaning 71.5% is water. The same goes for all the other parts of the crystallizer, such as the mother liquor. It is given that it's 18.2% sodium sulfate, so 81.8% is water. And for the product, even if it's not mentioned in the problem, but in the actual um, block diagram given by the problem, it is actually mentioned that 44.1% sodium sulfate is given out. So meaning 55.9% of that is H2O. So what we're going to do here first, since all these are already filled out, we need to take and check on the dye element that we have. So we already have water and H2O. The easiest for us to solve is in this problem is to solve first the kilograms, actual kilograms on the evaporate, since there is no sodium sulfate that goes out or evaporates on the evaporator. So it is mentioned that 5% of water is evaporated from the originally present water. So for us to be able to solve this one, we need to multiply first 7,500 by 71.5 because originally it's 71.5% water. Then we need to multiply it by 5.05 because 5% of it has already evaporated. So we already have 268.125 kilograms of evaporated water. So the general formula for crystallization is actually feed is equal to mother liquor plus evaporate plus product. So what actually happens here is that what goes inside the feed must go out on all these areas. So for us to be able to easily account all these, I will just use variables A, B, C, and D. So let us first solve for solute balance or the sodium sulfate balance. So since there is no sodium sulfate going out to the evaporator, we don't need to include it in the equation. So what happens is that 7,500 multiplied by 28.5% sodium sulfate is equal to sodium sulfate that goes out of the product. It's 44.1%. Then addition to the sodium sulfate content on the mother liquor, that's 18.2%. Now we already have our first equation with two unknowns. Next is we're going to account the water that goes out. So we already have accounted the water that went out to the evaporates. Now we're going to account B and D, including C. So 7,500 going to multiply it by 0.715 is equal to 268.125 kilograms. That is the water going out as evaporates. Then plus B, then multiply B by 0.559, then plus D 0.818. So same as the first equation, we also have two unknowns for this one. So for us to solve this, I'm going to show you how you're going to place it or solve it using your calculator. So to solve for two equations with two unknowns, we're going to click mode and choose one because that is two unknowns. So we're going to input the equation. So the thing that we need to understand with this one is that we're going to place the constant on the C, then the variables with unknowns on A and B. So we have our first equation. We have 0.441, then 0.182, Then our constant 7,500 times 0.285. There. Then we go to our second equation. We have, so for this one, since we have a constant here, what we need to do is to transfer it to the other side of the equation and subtract it to 7,500 times 0.715. So, point, the value for B is 0.559. What you also need to remember is that when you try to place the values in your calculator, you need to remember which um, missing values that variable that you place first. If it's B here, you're going to also place B on the second equation first. So 0.559, then 0.818, 818, there. Then we're going to is the constant 7,500 times 0.715 subtracted by the value of C, which is 168.125, and hit equals. So we already have the first value, the value for B, which is 3,171.038, and the value for D, 4,060.884. So we already have the values for the two missing variables. So we already have the weights of B, then C, then D. So that is how you're going to solve for crystallization problems.
A plant produces 30,000 metric tons of anhydrous sulfate annually by crystallizing sulfate brine at 0 degrees Celsius. Yields of 95% and 90% in the crystallization and calcinations operations are obtained respectively. How many metric tons of liquor are fed to the crystallizer daily? For this question, we must note that there are 300 working days per year.
To illustrate, here is the process flow diagram involving the kiln and crystallizer, although our focus will be on the crystallization process. Given the mass of anhydrous sulfate produced annually, we can use the mass of the equivalent sulfate brine, which is also known as sodium sulfate decahydrate or Glauber salt, being fed before getting the mass of the liquor by its solubility. Since solubility is not given, we find it from other sources such as Perry's, and so we can see that at 0 degrees Celsius, the solubility of Glauber salt is 5 grams per 100 grams water, which is just equal to 5 metric tons per 100 metric tons water. We begin with conversion from per year to per day, since it's what the problem asked for, and given its equivalent working days of 300. Then, we convert the mass of anhydrous sulfate to moles, so that we can in turn find the actual mass of Glauber salt fed to the crystallizer. It is through balanced equation that we get the ratio that per mole of sodium sulfate decahydrate, we have 1 mole of sodium sulfate and 10 moles of water. Now that we have the mass of Glauber salt fed per day, we go back and use the solubility, in which the liquor solubility is the sum of the two, of the salt and the water. And then we must take note that the crystallizer has only a yield of 95%, which means it is only 95% of the feed. So we have to divide it by 0.95 to get the mass of liquor fed to the crystallizer, which is 5,012.60 metric tons per day. Problem solved. evaporator is required to concentrate a solution from 10% solids to 30% solids at the rate of 250 kg of feed per hour. If the pressure in the evaporator is 77 kPa absolute and if steam is available at 200 kPa gauge, calculate the quantity of steam required per hour and the area of heat transfer surface if the overall heat transfer coefficient is 1700 joules per meter squared second degree Celsius.
From the problem, we have our illustrated flow diagram composed of our feed F of 250 kilograms per hour of 10% solid, producing a concentrated liquid L composed of 30% solid, and evaporated water V. Our steam supplied to the evaporator S with a pressure of 200 kilopascal gauge pressure and produces a condensate S. Inside the evaporator, the pressure is 77 kilopascal absolute with an overall heat transfer coefficient of 1700 joules per meter squared seconds degrees Celsius. Our assumptions will be the temperature of the feed before entering the evaporator is 18 degrees Celsius, the boiling point temperature inside the evaporator of 77 kilopascals is 91 degrees Celsius, and the specific heat of the solution is 4.186 times 10 to the power of 3 joules per kilogram degrees Celsius. What is required in the problem is the quantity of steam required per hour and the area of heat transfer surface. To start the solution, we will refer to the steam tables to get the latent heat for both the steam and the solution. So from the steam tables, the steam pressure is 200 kilopascal gauge pressure, which is equal to 300 kilopascals absolute pressure, and the temperature of the steam is 134 degrees Celsius. This gives us the latent heat of 2,164 kilojoules per kilogram. For the evaporator at a pressure of 77 kilopascals absolute and the temperature of 91 degrees Celsius, we have latent heat of 2,281 kilojoules per kilogram. To get the mass of concentrated liquid produced and the vapor produced, we will do a mass balance equation. Starting with the overall mass balance equation, wherein the feed F is equal to evaporated water V plus the concentrated liquid L, followed by the solid mass balance. To get the weight or mass of L, we know that 10% of the feed is solid, so 10% times F equals to 30% of L. We plug in the value of F and we get the answer 83.33 kilograms per hour concentrated liquid produced. Going back to the overall mass balance, 250 kilograms per hour feed is equal to evaporated water plus the concentrated liquid of 83.33 kilograms per hour will give us the mass of the evaporated water of 167 kilograms per hour. From the data retrieved from the steam tables, we may now update our flow diagram for the problem. So the feed entering at 18 degrees Celsius will experience heating up to 91 degrees Celsius in the evaporator, while the steam entering at 134 degrees Celsius will experience cooling upon entering the evaporator at 91 degrees Celsius. We will now proceed to heat balance equations, wherein the heat entering is equal to the heat leaving the process. The heat entering the process is equal to the heat supplied by the steam entering the evaporator, while the heat leaving the process is equal to the heat required by the concentrated liquid. We will denote the heat supplied by the steam as Qs and the heat required by the solution as QL. So the formula for heat available per kilogram steam is equal to the latent heat of the steam plus sensible heat in cooling to 91 degrees Celsius. Since our steam enters at a higher temperature of 134 degrees Celsius and cools upon entering the evaporator of 91 degrees Celsius. The latent heat formula is equal to the mass times the latent heat of fusion or vaporization, while sensible heat is equal to the mass times the specific heat times the change in temperature. So the heat available per kilogram steam is equal to the mass of the steam times the quantity of the latent heat of steam plus the specific heat of the solution times the change in temperature. We will now plug in the values, wherein the latent heat is equal to 2,164 times 10 to the power of 3 joules per kilogram per hour. The specific heat is 4.186 times 10 to the power of 3 joules per kilogram degrees Celsius per hour. And the change in temperature from 134 degrees Celsius to 91 degrees Celsius. This will give us a final formula and equation of Qs equals to mass of the steam times 2.34 times 10 to the power of 6 joules per kilogram per hour. We will now proceed to the heat required by the solution QL, which is equal to the latent heat of the solution plus the sensible heat in heating to 91 degrees Celsius. Since the feed enters at a temperature of 18 degrees Celsius and experiences heating upon entering the evaporator of 91 degrees Celsius. Plugging in the values, latent heat, which is equal to the mass times the heat of fusion or vaporization. In this case, the mass of the vapor, 167 kilograms per hour, times the heat of 2,281 times 10 to the power of 3 joules per kilogram per hour, plus the sensible heat, which is equal to the mass times the specific heat times the change in temperature, wherein the mass is 250 kilograms per hour times the specific heat of 4.186 kilojoules per kilogram degrees Celsius per hour times the change in temperature from 91 degrees Celsius to 18 degrees Celsius, which will yield a heat required by the solution QL equal to 4.57 times 10 to the power of 8 joules. Equating the two heats, Qs equals to QL, will give us the equation mass of the steam times 2.34 times 10 to the power of 6 joules per kilogram per hour equal to 4.57 times 10 to the power of 8 joules, giving us the mass of the steam, 195 kilograms per hour. In calculating the heat transfer area, we will use the formula Q equals to U A delta T, where Q is the heat required by the solution, U is the overall heat transfer coefficient, A is the heat transfer area, and delta T is the change in temperature. We now have Q, U, and delta T. Plugging in the values, we will get 4.57 times 10 to the power of 8 joules equal to 1,700 joules per meter squared seconds degrees Celsius times the area times the change in temperature, 134 degrees Celsius minus 91 degrees Celsius, giving us the area of 1.74 meters squared.